Hello everyone, welcome to the April 16th edition of Math Stats. Reminder that your exam P number 3 solutions are due Friday. So for this exam, I'm not going to make you take it whenever you need to prepare for the P exam, but this way we still have solutions for it. All right, let's begin. Today we're going to learn about the chi-square goodness of fit test. Now, this test was first proposed by Carl Pearson in 1900. And this test you're going to find essential for comparing different distributions of people. But we will get there. So let's begin with the binomial variable. Let's suppose that I have a random variable y1 that has a binomial distribution with n trials and probability of success, p1, where the probability of success is between 0 and 1. We know that the mean of y is just n times p1, and the variance of this variable is n times p1 times 1 minus p1. And furthermore, we know that if we write the variable z equal to this expression right here, by the central limit theorem, this is approximately normal with mean 0 and standard deviation 1 when n is large. All right, typically when we say n is large, we mean that this is bigger than 5 and this is bigger than 5. These are the conditions that we verify. All right, so what does this tell us? Well, if we let q1 equal z squared, this tells us that q1 is approximately a chi-square random variable with 1 degree of freedom. So that was something we proved in Math Prob, that the square of the standard normal has distribution equal to chi-square with 1 degree of freedom. So we're going to do the following. We're going to let y2 equal n minus y1. y1 is the number of successes, y2 is the number of failures, and p2 is 1 minus p1. So if we do a little algebra, we see that we get the following. So if we did a little more algebra, you would find that this is actually equal to y1 minus np1 squared over np1 plus y1 minus np1 squared over n1 minus p1. And if you do a little more algebra, note that y1 minus np1 squared is n minus y1 minus n times 1 minus p1 squared. This is the same as y2 minus np2 squared. So what that tells us is that expression we wrote above is equal to y1 minus np1 squared over np1 plus y2 minus np2 squared over np2. So that's the expression we get for q1. What we notice is that the first numerator is the expected value of y1. Well, we see that that part of it is appearing right here. And the expected value of y2 is n times p2, which we see right here. So the numerators of these two expressions are basically showing you how much does the actual number of successes differ from the expected number of successes squared, and the same for failures. So each numerator consists of the square of the difference of the observed number versus the expected number. So this would be the observed number of successes, and this is the expected number of successes. All right. So we've seen that this is intuitively approximately a chi-square distribution with 1 degree of freedom. In some sense, Q1 measures how close the observed numbers are to the expected numbers. So for example, if y1 and y2 were equal to their expectation, then the computed value of Q1 would be 0. If they differ a lot, this expression will be big. So a remark, if y1 is close to np1 and y2 is close to np2, this would tell us that Q1 is small. But if y1 is far from np1 and y2 is far from np2, this would tell us that Q1 is big. All right, so that's great, but we want to generalize because often when we are collecting data, we're not just collecting data that has two categories, male and female. That's got two categories. But for a lot of your work, you dealt with distributions where you had multiple categories. It could be when someone decided to become a math major, middle school, high school, college. That's 3 categories. Or it could be something like major, where there's far more categories than that. So we're going to generalize. And this is what we really need for our projects. We're going to let an experiment have K mutually exclusive and exhaustive outcomes. And we call these outcomes A1 through AK. For example, if it is what's your favorite season, there would be 4 outcomes: fall, spring, winter, and summer, and those are the only ones. And since someone's picking their favorite season, they can only pick one of them. We let PI equal the probability that someone picks one of these categories. We perform a random experiment n times. And yi equals the number of times the experiment results in category AI. For example, if you're asking people what's their favorite season, how many of them said fall is their favorite season? So the distribution of y1 through yk minus 1 is what we call a multinomial distribution. It's the natural generalization of the binomial, and we need to do a variety of things to fix it. So if we want to know what the joint PMF is, what's the probability that I know what y1 through yk minus 1 are equal to? It's the probability that exactly y1, picked category A1, all the way up to yk minus 1 equals yk minus 1. And we know these numbers are all non-negative. So you might be wondering why we dropped the kth term. Well, that's because we know that they all must add up to n. So this tells us that if I know what y1 through yk minus 1 are, I already know what yk is. It's kind of like saying I surveyed 100 people. I know how many people picked fall, winter, and summer as their favorite seasons. Therefore, I already know how many people pick spring as their favorite season without being told. Okay. Furthermore, the probability of a particular arrangement follows the multinomial distribution. All right. And we say that y1 through yk have a multinomial distribution with parameters n and p1 through pk. So knowing this multinomial distribution, we can write an expression that was very similar to when we wrote when we had binomial distribution, where the numerators are the difference between the observed number of experiments that resulted in category I squared over the expected values. So the numerator is the square of the difference between observed and expected, and the denominator is just the expected number of observations for a particular category. So what Pearson proved, it's hard to do, we're not going to do it in this class, is that this is actually a chi-square random variable with k minus 1 degrees of freedom. So the question is, when can we use this approximation? You can definitely use it if n times pi is bigger than or equal to 5 for all I. That's not the only time you can use it, though. The thing you want to worry about is you want to avoid using this approximation when some particular NPI is so small that the expression dominates the sum for q k minus 1. And we'll have an example of that later where that is the case. Okay, so now we want to proceed by doing a hypothesis test. So how do we do a hypothesis test with this newfound information? Well, we want to test the hypothesis that we know what all of these values are, all of these probabilities are, against the alternative that one of these probabilities is off. So you see that the alternative hypothesis is very multi-sided. So in order to do this hypothesis test, we take a random sample of size n, and we're going to record the number of times that AI occurs. Okay, so what we do is we then take this sum where we take the observed number of results in category I minus the expected number over the expected number. So if this is small, we'll accept the null hypothesis, and if it's large, we'll accept the alternative hypothesis. Okay, so that's enough talk. And oh yeah, the cutoff though, before we move on, the cutoff is the value chi-squared of alpha with k minus 1 degrees of freedom, where alpha is the significance of your tests. Okay, so that's enough talk of that. Let's move on to some examples. So let's look at the US population and break up into different categories. We have the age group and the proportion of people in that age group. So under 5, 5 to 14, 15 to 29, 30 to 44, 45 to 59, and 60 and up. Okay, so most strains of the flu affect older people more seriously than younger people, but an exception was the swine flu of 2009. In 2009, there were 619 reported swine flu deaths in May of that month, of May of that year. So using these same age groups, let's show what they were equal to. So by age group, we had the following number of deaths. So we want to test the null hypothesis that the distribution of ages of swine flu victims follows that of the US population. And the alternative hypothesis will be that that's not true. In order to do this hypothesis test, we need to calculate the expected frequency. So the expected frequency is actually pretty easy to compute. We just take the n, so n is 619, and we multiply it by the proportions of the population. So the expected number of deaths for each age group following the same age groupings as before would look something like this. And notice that we're going to use them as decimals. All right, so what we do is to calculate our chi-square statistic, we need to add up these 6 quantities. And so what we do is we take the observed number of deaths, 51, minus the expected number of deaths, 49.52, square it, and then divide by 49.52. Second category, we observed 204 deaths, minus 68.09 expected over 68.09. And we continue in a similar fashion. And if we add that all up, we will get a value of 568.13. So the chi-square significance critical value for 5 degrees of freedom is 15.909. So this is obviously much, much bigger than our cutoff statistic, which means we're going to accept the alternative hypothesis and reject the null. We can also do this on RStudio. So let's share that screen. Okay, so what you see here is I have put our data values in the first piece of the first vector called data, and I've put the probabilities in the second one. And so the way that you do such a test is you do chi-square.test of your data values, and you write P equals your probs, and it calculates the chi-square test, and you see the degrees of freedom, the chi-square value, and the p-value, and you see the p-value is very small, which is what tells us that we're going to reject the null and accept the alternative hypothesis. So after all that, what has it told us? It's told us that we conclude that the distribution of ages of swine flu victims differed from the US population. And we're very confident of that. The problem with the chi-square test is that it's many-sided. We're very confident that the distribution of swine flu victims was not the same as the distribution of ages from the US population, but we don't actually know what's true though. Is it really true that younger people were affected more, or were older people affected less? We don't really know, and that would require a different kind of testing. In practice, experimenters often look at linear functions of our random sample, but this is beyond the scope of this class. All right, so that's that one. Let's take a look and move on to another example. All right, so let's have a new example. And this is an example where we're going to test whether the data follows a certain distribution. For example, does it follow a binomial distribution? So you've been playing D&D a lot with your younger brother, and he frequently casts a certain spell on you. You roll 5 dice, and you fall asleep. Well, your character falls asleep. Your character falls asleep if you roll 3 or more ones and twos combined. You're convinced that the dice have been weighted, but you need a test to find out. You roll the 5 dice 100 times and record the total number of ones and twos on each roll. And you get the following frequencies. So number of ones and twos rolled, and the frequency. Okay, so we know that there are 6 possibilities. You could roll 0, 1, 2, 3, 4, or 5 ones and twos combined, and you get the following frequency. So we know that X should be binomial with n equal 5 and probability 1/3. Ones and twos make up 1/3 of the possible dice numbers, and so the probability of rolling a 1 or a 2 on a given roll is 1/3. So we produce the actual distribution. Here's the theoretical frequency. And the expected frequency on 100 rolls. Let's see, this would be 0.132, 0.329, 0.329, 0.165, 0.041, and 0.004. So on these rolls, on these 100 rolls, we'd expect to get 13.2, 32.9, 32.9, 16.5, 4.1, and 0.4. So we're going to calculate the Q5, and then we're going to talk about some problems with it. So if I calculated Q5, it should be the observed number of rolls, 10, over the expected number squared, plus the observed number, 22, minus the expected number squared, plus the observed number, 34, just a couple more left. And we get a chi-square value of 26.784. And the cutoff value for a 5% significance test is 11.0705. So this would tell us that we reject the null hypothesis and accept H1. But there's a caveat. Look at these two values right here. They're both smaller than 5. Those are these two terms right here in the sum of our chi-square distribution. So if we observe, you note that 7 minus 4.1 squared over 4.1 plus 3 minus 0.4 squared over 0.4 is 18.95. That's a very large percentage of our chi-square value. Therefore, we should be wary of concluding too much from this experiment. Okay, thus far, all the hypothesis tests we've done with the chi-square statistic Q sub k minus 1 have been simple ones. That is, we have a particular value in mind. But this is not always the case. Frequently, the probabilities are functions of one or more unknown parameters. For example, in this previous example, X was a binomial variable with 5 trials and probability that we did not know. So the probabilities were of the form 5 choose I, p to the I, 1 minus p to the 5 minus I, where we did not know p. So one way to get around this difficulty is we could estimate p using the information we have. So we often call these estimates p tilde. And we want to find a p tilde that minimizes our chi-square value. So there should be some p tilde value that makes our sum as small as possible. We call this p tilde a minimum chi-square estimator. If this p tilde is used, we need to adjust the number of degrees of freedom. In our previous example, Q5 is still chi-square, but now it actually loses another degree of freedom and becomes chi-square with 4 degrees of freedom. Note, if we estimate d different parameters, our qk minus 1 is chi-square, where we reduce the degrees of freedom by d. Okay, it's usually pretty difficult to find the minimum chi-square estimator, but we can actually do it for our example above. So in our example above, we knew, let's call this function g of xp, and that's the binomial distribution where you have x successes, 5 trials, and probability of success p. So we know that our Q5 is equal to the observed frequency minus the expected frequency divided by the expected frequency. I'll do another one before I just put a dot, dot, dot. So I don't know what this is equal to, but there's an expression using the formula for the binomial distribution. And we keep going until we get to the end. And we want to find where this is minimized, but this is a function of p. So how do we find where something's minimized? We take the derivative and set it equal to 0, and we get that p tilde is equal to 0.4149, which leads to a Q5 value of 4.546. And the chi-square critical value for 4 degrees of freedom is 9.488. And so here we would accept the null hypothesis that the distribution is binomial with probability of success 0.4149, which is not great for your brother because this means we accept the null hypothesis that the dice were loaded. Okay, so that was an example where we thought our distribution was a binomial distribution, but we didn't know what the probability was. You can pick a single probability and do the hypothesis test, but it's often better to try to estimate it some way. So the method we used was the minimum chi-square estimator, but that can be very difficult to find sometimes. So the last 2 examples we're going to talk about are ones from the book. This example 9.1-3 in the book. And in this case, we're going to use the chi-square test to determine whether the Poisson model is a good fit. For our data. Okay. So what's happening? So x is going to equal the number of alpha particles emitted by a sample of barium-133, a radioactive isotope, in 1/10 of a second, counted by a Geiger counter. Okay, so we have 50 observations. And let's take a look at them now. So these are the 50 observations, and we're going to test the following. We're going to test the null hypothesis that X is Poisson against the alternative hypothesis that X is not Poisson. So if you take all that data, what you'll find is that the sample mean is 5.4. And that's what we're going to use as our mean of our Poisson distribution. So we need to do something else before we continue. See, we have lots of different possibilities. A Poisson distribution can have 0 observations, 1, 2, 3, infinitely many. So what we have to do is we have to partition the set of outcomes for the experiment into sets. And so we're going to pick these sets to be A1 will be the possibility that your Geiger counter counts 0, 1, 2, or 3 observations. A2 will be the possibility that your Geiger counter records 4 observations. A3 is 5 observations. A4 is 6 observations. And A5 is 7 observations, that is 7 particles emitted, and A6 is just going to be 8 or more. Okay, so why do we have to combine these into groups? We had to combine these into groups so that the expected number of outcomes for each set would be at least 5 if the null hypothesis is true. Okay, so I'm going to show you the table that gives us the observed frequencies, the theoretical probabilities, and the expected frequencies. Okay, so here's the table. So this category here under A1 says that we had 13 observations in category A1, which was 0, 1, 2, or 3 alpha particles. We had 9 observations in category A2, which was 4 particles detected, and so forth. Below that, in the second row, you see the probabilities of, in a single experiment, how many observations should fall into each of those categories. And we had 50 of them. And so you see the expected number of observations in each category in the third row. So we calculate the chi-square value. And what we're going to observe is we're going to have 6 minus 1 minus 1 degrees of freedom, because we used an estimate for the type of Poisson distribution we are dealing with. So we subtracted this extra one because we used the sample mean. To approximate the mean of our Poisson distribution in the null hypothesis. So if we calculate this using R, we would calculate that Q5 is 2.763, which gives us a p-value of 0.7364. Obviously, we do not reject the null. This means we accept the null hypothesis that our data follows a Poisson distribution. Okay, so that was great. That was a discrete distribution where you had infinitely many possibilities. So the last thing we want to do is how can we use this goodness of fit test to consider a continuous type distribution? So how do we handle a continuous distribution where you're not going to have any two observations in the same, they're the same? So in the case of our Poisson distribution, when we are constructing these different possible groupings, we had a certain number of outcomes in each grouping. But now, for continuous variables, we're going to break up the range of all integers, all real numbers into different intervals, and those intervals will be our partition. So for a continuous type distribution, what are we going to do? We're going to partition the set of all possible x values into k sets or subsets. And so they will look something like this. The first one will be from the interval from -infinity to a1. The second one will run from a1 to a2. ak minus 1 will run from ak minus 2 to ak minus 1. And the last partition will run from ak minus 1 to infinity. And so we let yi equal the number of observations that fall in category AI. And we proceed just like we did before. We let our chi-square statistic equal this sum. And it's approximately chi-square with k minus 1 degrees of freedom. So I'm not going to work the last example. This example 9.1.5 in the text. But I think it shows you a lot of what you want to know. So if we look at our table here, here are our data points. And these are times between calls to 911. And what you'll notice about them is that they partition them into these different classes on the left. You'll see the frequency and the probabilities and the expected number of waiting times on the right. So you see that you partition the numbers from 0 to infinity into smaller categories. So to summarize, all of these tests we've learned are under a more general name of goodness of fit test. Because we're seeing how well does our data fit with a prescribed model or distribution. That is, how good is the fit? In particular, the tests in this section are all chi-square goodness of fit tests. Because they all use the chi-square distribution. So we'll get some time practicing this on Thursday, and you're going to find this very useful in your projects. Let me know if you have any questions.